Today I'm going to talk about how to handle interactions in linear regression models. And first, I want to cover a little bit about what a statistical interaction is conceptually. We say that there's an interaction when one predictor's association with the response variable depends on the value of another predictor. Another word for interaction is moderation. These two terms refer to the same concept. As an aside, one of the most frustrating things about statistics is that there are many words for the same thing, and even inconsistencies in how these words are used across fields and contexts. If you're ever not sure what someone means by a term, even a term that you commonly use and are familiar with, you should just ask them how they're using it, because it's totally possible that they have a different meaning in mind than the one you're accustomed to. When there's moderation, there's an interaction. These terms refer to the same basic phenomenon going on with the data. We also say that one variable moderates the relationship between two other variables. So you can turn moderate into a verb. The first sentence on this slide could then say one predictor's association with the response variable is moderated by the value of another predictor. I'm going to start with a simple example that I've stolen from Jack video. Jack claims that ice cream and beer are two of his favorite things. So he wants to test how they make him feel separately and in combination. He's going to do an experiment where on different days, he tests out a neutral condition where he has no ice cream and no beer, an ice cream only condition, a beer only condition, and a condition where he has both beer and ice cream. Here are the results of Jack's experiment. By testing all four conditions, he has learned something that he wouldn't know otherwise. As expected, Jack feels happy when he has ice cream and happy when he has beer, but he feels sick to his stomach if he has both ice cream and beer. If he has not had any treats so far, then having ice cream will make him feel better. But if he has already had some beer, then having ice cream will make him feel worse. So the effect of ice cream is completely different depending on the presence or absence of beer. If Jack only tried eating ice cream and drinking beer separately, then he would notice that both of them made him happy, and he would assume that having both at the same time would make him doubly happy. An interaction happens in just those cases when you don't get the effect that you would expect by just adding the two things together. As a reminder, another word for interaction is moderation. So you could say that beer changes or moderates the effect that ice cream has on Jack. Beer is a moderator of the effect of ice cream, and ice cream is a moderator of the effect of beer. We might also represent Jack's situation like this. The teal squares represent the case where Jack has no beer. In this case, his happiness is moderate if he has no ice cream on the left, but high if he has ice cream on the right. The purple circles represent the case where Jack has beer. In this case, he's happy as long as he has no ice cream on the left, but his happiness becomes very low if he has ice cream on the right. And if we connect the dots, you might notice that one way to tell that this is an interaction is that the lines are pointing in different directions. Their slopes are different. The teal line, with a positive slope, shows that ice cream improves happiness, and the purple line with a negative slope shows that ice cream hurts happiness. This is a clear sign that the answer to "does ice cream make Jack happy?" is "it depends," and therefore that there is an interaction. An interaction arises when one predictor's association with the response variable depends on the value of another predictor. So in this example, if you ask, "Does ice cream make Jack happier?" if the answer had simply turned out to be yes, and always by the same amount, then that is not a sign of an interaction. Even if beer made Jack happy too, as long as you don't need to know whether he's had beer or not to decide whether ice cream will make him even happier than he already is, then there's no interaction. But in our example, the real answer to "does ice cream make Jack happier?" is "it depends." If you ask a question about one variable, and you find that the answer depends on a totally separate variable, then you're in interaction territory. People often reasonably distinguish between two types of interactions. In an interaction, the effect of one variable on the outcome depends on the value of another variable, and in this example, we're interested in the effect of coffee on your morning math test, and we're interested in whether it might depend on whether you've had breakfast that day. In one type of interaction, shown on the left, the moderator reduces or exaggerates the effect of the main independent variable of interest. For example, perhaps having breakfast enhances the benefits of coffee, so that if you haven't had breakfast, then coffee helps your test score a little bit. But if you've had breakfast, then the coffee will really help you a lot. Coffee always helps, but not always by the same amount. Sometimes the moderator may even reduce the effect to zero, like if skipping breakfast meant that coffee wouldn't have any effect on you at all. In the other type of interaction shown on the right, the moderator reverses the effect of the main independent variable or predictor of interest. For example, perhaps coffee actually hurts you if you haven't had breakfast. It makes your stomach hurt and screws you up on the test. But if you eat breakfast, then the coffee helps your test score because the caffeine helps you concentrate. In this scenario, coffee can help you or hurt you, depending on whether you have breakfast. Most people call this a crossover interaction because, for example, the effect of coffee crosses over from good to bad. Now let's talk about how to actually test an interaction in a conventional statistical model. Here's the regression equation format you should be used to by now. If we've got two predictor variables, we model the response variable y as an intercept, b0, plus a slope times the first predictor, b1 times x1, plus another slope times the second predictor, b2 times x2. And of course, there's a residual term indicating how far off the resulting estimate is from the actual values of y. And when we fit the model, what we're doing is minimizing the sum of squared residuals. To add an interaction between the two predictors, all you do is include a third variable in the model, and that third variable is the product of the two predictors. The product of x1 and x2 just works like its own variable. The math of regression doesn't care that it's x1 times x2. You could even call it x3 or product if you want. But it's always much easier for us humans to keep track if we explicitly mark where it came from. This product term gets its own separate slope, which I've marked here as b3. So the observed variables are y, x1, and x2. And the product of the two main predictor variables, x1 times x2, is treated as another observed variable. The model chooses four parameters, b0 through b3, that minimize the sum of squared residuals. b0 is the intercept. b1 and b2 are conditional slopes with a special interpretation that we'll get to in a minute. And b3 is the slope of the interaction term. Usually the first thing that I look at when I'm seeing the output of a model like this. If b3 is statistically significant, then that means there is a significant interaction. In this example, I'm testing an interaction between participant age and wealth. I'm showing the product term here using a colon, age colon wealth, because that's how R displays such terms in regression output, and I want you to get used to it. This is literally the product between age and wealth in the data. It doesn't matter if age is in years and wealth is in dollars, and multiplying years by dollars results in huge numbers with unintuitive units. The point is that the product allows us to test an interaction, and we're mostly going to focus on the units of the lower order terms anyway. As always, when you fit a model, you'll get a table with a row for the intercept and rows for each slope. Each row shows values for the parameter estimate itself, b, the standard error of that estimate, se, and a t-test of the difference between that estimate and 0. In this case, the age by wealth interaction is statistically significant. You can write out the regression equation using the literal numbers and variables from the model. So the score on whatever the response variable is in this quick example is equal to 9.1, that's the intercept, minus 0.7 times age, plus 0.3 times wealth, plus 1.2 times age times wealth, plus, of course, the residual. Suppose that we wanted to understand what this negative 0.7 means for age. It's pretty hard to figure it out by trying to consider all these terms at once. Luckily, we have a handy strategy available. That strategy is to imagine what happens when wealth is equal to 0. So here's the equation again with all the terms, and here's what happens if we're imagining someone with 0 wealth. Their debts cancel out their assets and their wealth comes out to exactly 0. It's a reasonable point to consider along the continuum of wealth in our hypothetical study. Plenty of people have close to 0 wealth in real life. So I've filled in 0 for wealth in the equation. 0 multiplied by anything is 0. So both of these terms are 0, regardless of what age is and regardless of what the slopes are. When wealth is 0, the fitted value of score is 9.1 minus 0.7 times age, straight up. There's nothing else left in the equation besides the residual. This is the key to understanding what the slope for age means in this model. Earlier I said it was something called a conditional slope, and we'd come back to it. Here we are. The negative 0.7 for age represents the linear relationship between age and score at the point where wealth is 0. Remember, this is an interaction, so there is no longer just one relationship between age and score. Instead, the relationship between age and score depends on wealth. And this parameter estimate tells us that for people with 0 wealth, the score goes down by 0.7 for every additional year of age, on average. Negative 0.7 is the conditional association between age and score given 0 wealth. It's also called a simple slope of age at 0 wealth. Let's talk about terminology for a second. When I look at a regression table like this, with an age by wealth interaction included in the model, I think of the slope for age as the relationship between age and the response variable at the point where wealth is 0, and the model assumes that this relationship varies continuously along the spectrum of wealth. And it's nice to have a term for this negative 0.7 from a lower order term in a model that includes a higher order interaction. What should we call it? A conditional association is a good general purpose term. Some people call it a simple slope. That's also reasonable. If the study is experimental, you might call it a conditional effect or simple effect. Really, you can use any combination of conditional or simple and association, slope, or effect to describe this kind of value. So when we are thinking about regression interactions, when one variable is 0, we can interpret the slope of the other variable. And changing where one variable hits 0 changes the slope of the other variable. So we will want to strategically adjust where one variable hits 0 and watch how the other slope that it's interacting with changes. That will enable us to understand the interaction. In the next video, I'm going to be demonstrating some of these concepts by showing you actual code and output in the R statistical computing environment.